the introduction. So today, we're going to be talking about this kind of hectic sort of novel numerical hardware design methodology that our group has come up with. So we're a team that's in Intel graphics, so we're the people coming up with all the machine learning problems and coming up with hardware to kind of solve these problems that people in this room, I'm sure, are coming up with all sorts of problems for us to solve. So in general, graphics hardware is a bit weird. Basically, at the end of the day, your test of correctness tends to be something like, does it look good on a screen? And writing that down in the specification is clearly rubbish. DX has had a good go at it, but there's lots of weird things. So in this example, we just got some sort of eigenvector calculation that we actually put into hardware. It's got a DFG that looks something like this, but you basically have this hell zone of what is your algorithm you're going to choose, what components are you actually going to go and build. You've then got all this complication of what precisions you might need these components to be. Then after all those decisions that all have massive consequences, then you actually have to go and think about, building your hardware. What's your RTL given this sort of problem setup? And this takes months and months and months and months. So in general, what state of the art kind of looks like is, we have natural language specs. These are kind of terrifying. We have no number formats. They're all kind of real. We generate some non-bit accurate C model that we go and simulate, and then we do tons and tons of optimizations at the RTL level. You don't need timing, let's go back around, or you've got this bug, and again and again. So from the kind of perspective, you've got this top-down optimizing your hardware with respect to all these different decisions, where the top level of these decisions, you've got kind of the most power to actually affect change on the quality of the design and on the resulting hardware. But at this bottom level is actually where we spend most of the time churning and making the quickest decisions. So the rate of change of all these things is really weird. And at the bottom, you have to satisfy this application level correctness, whatever the hell that means. So in our group, we think this is kind of a nice PLARCH study here, because we have this guy, Bill Zorn, who is a PhD in kind of programming languages. He comes out of Zach Tatlock's group. And he's kind of working his way from his research, pushing down, thinking about how do we express algorithms and all this sort of stuff. And then on the other hand, you've got people like me who are kind of pushing from research, pushing upwards. PhD with a question mark, because I'm still doing my PhD. Hopefully it turns into not a question mark. But basically kind of pushing our way upwards. And then our boss, Theo, Drane, who some of you may know, basically said, well, you two should really meet in this middle ground and say, what if we can actually specify, simulate, model, implement, and optimize all these thousands of designs within a day? It sounds impossible. We can say it might work. We're going to try and present a methodology that hopefully does work. So what do we talk about specifications? Then obviously we've got all these number formats. We've got multiple precisions that we might be interested in. We've got actually the right answer. What the hell is that? In general, how do we compute things that are in reals? And then how do we actually execute these things? And, as Alistair, I'm sure, presented this morning, machine-readable specifications can be a really powerful way to do that. So this is when we settled on this FPCore language that was developed at the University of Washington in Utah. And it basically allows you to express tons and tons of different sort of precision annotations really easily. So in this basic example, all I've got is I want to try and implement A times B plus C plus D. And from a hardware perspective, there's no limits on actually what components we can build. We can do this as like multiplication and then additions and additions with all the rounding in between. We can do this as FMAs and additions. There's no real limits, but each of these decisions introduces where are you going to do your rounding and all this sort of stuff. And so what we want is some mechanism to go and explore all these different hardware implementations, but kind of at that higher level, and where we can also, crucially, play with these precision annotations. So how much precision do we want to put in? And this is where FPCore has these nice opportunities to go and annotate each operation. So here we have some float precision annotation that says it can either be 5 bits of experiment in total of 8 bits, like 3 bits of Mantis or 2 bits of Mantis. This is kind of not my speciality, so be kind on this stuff. But also we've got this kind of real annotation, which is slightly complicated, and I don't fully understand it, but basically it means that you avoid all the rounding and you kind of defer that rounding to the end, giving you some notion of able to express these like complicated operators that maybe Bill doesn't support in FPCore, like a 3-input addition. Then we actually want to go and simulate these things. So here we use the MPFR to get some arbitrary precision rounding. So this is a real nice way. We can just get loads of different information. And what we can take from that is we can do real easy application level visibility. So what you can see is you've got the kind of, the green is your golden reference model, which you definitely can't see on this screen, but oh well. We've also got the red, which is what maybe our current implementation is, and we've got this blue design, which is representing our, our proposed implementation, this FPCore thing, and what the green and blue ellipses are showing that, as you're tuning this precision, as you're increasing this precision, you're basically getting this ellipse better and getting it closer to the correct, the real implementation. Just trust me that those blue and green ellipses overlap. And then probably one of the nicest things about FPCore is it allows us to go and explore all these different precisions really easily. So you'll see here we've got all these different precision annotations on this code. And what we can do is we can just sample and run some tests and see how far off we are. So on the left-hand side, we've got some average number of correct bits, but actually in this design we have 16 bits of precision. So what's interesting is that we see that down the bottom here we've got some dummy cost metric that's saying, actually in this case it's just the sum of all the bits, so the total number of bits we use, which is a really dumb cost metric, but it should give us some notion of what's going on. And you can see that basically we can't get past 10 bits of precision. So even though we're adding hundreds of extra bits of internal precision, we can't get any further. We can't get 16 bits correct when we really think we should be able to. So basically that just tells us that our algorithm is numerically unstable. You've got some inherent instability in there, and it's just a bad algorithm. Don't implement that. Then if you go and change your algorithm, you start to see this Pareto curve emerging. So you can see on the right-hand graph, we've got this nice frontier emerging where as we're adding more bits, yeah, it's working. We're actually seeing what we want to see. We can get it to 16 bits of precision. And these are all simulatable in like under 2 hours, and you do far faster simulation than you can do with other RTL and things like that. So we've kind of talked about this whole IFP stack where we can do that simulation, the tuning, and then Bill has developed recently this compiler that can basically generate from FPCore into some C++. And this C++ is kind of highly templatized, and it's meant to be formal friendly, namely we can go and throw it into our existing formal tools that we get from Cadence and whoever and Synopsys, but also meant to be bit accurate. And so that means we can then compare that and have that as our golden reference model. For templates, he uses, if we have a floating point adder, he's developed templates to fill in what those operators should be. So here you see some complicated templated looking C++, all beyond me as a hardware designer. I just write integer operations and stuff. But what's nice is that because we have this compiler, we can extend it, and has been extended to things like ASL that was presented this morning, and starts to look at maybe we can extend this to System C, to RTL. We could generate kind of whatever we want out of these things. So now this is kind of we've got this nice C++, how wonderful. We can start talking about things like HLS. And HLS is good, it does some cool stuff, but in reality, it doesn't match what a human can do. It doesn't match what the human is optimizing, certainly in graphics where we're stamping out thousands of these designs, how many CUDA cores do you have in your GPU that you've got at home? Area and power and performance count for so much because we're going to duplicate it so many times. And so at the moment, HDL or HLS hasn't really caught on in the graphics domain, mainly because it just can't achieve the performance of hand-tuned designs. So what we really want to get is further down this road and get down to our best performance, to our kind of maybe hand-tuned HDL. So this is where kind of my research comes in, which is what I'm more comfortable talking about, which is how do we actually get from this left-hand side that's maybe something that might come out of our compiler into the right-hand side, which is going to be some efficient hardware that's got, on the left-hand side we've got 277 bits, on the right-hand side we're just using 25 bits everywhere. This results in, way out faster hardware, all this sort of good stuff, but it's a bit of a nightmare actually to get from the left-hand side to the right-hand side. Because basically what humans are doing is doing kind of value range analysis. They're working out what's the number of bits they need for each of these operations and doing rewriting as they go along. And so that's where we developed this rover toolchain that is basically looking at how can we take RTL in, do some rewriting in what's called an E-graph, so equivalence graph, which allows us to express tons and tons of different equivalent representations of our RTL, but also combine that with program analysis that allows us to do optimizations exactly like on this top left-hand side. So this is what's being presented in DAC in a few weeks' time, is how we're able to use this toolchain with all this value range analysis to actually extract out, a very efficient floating point adder design that's 33% faster and 41% smaller than what you might get out of a compiler like this left-hand side. And in this framework, obviously this gives us the opportunity to play with what's the best area, what's the best power, best delay. We can explore all these different kind of axes within this framework. And so this is what Theo believes is a one-day operation. We can basically take this through to FPCore, do the exploration there, run the simulations, do our visibility, run our precision tuning to figure out what different precisions we're interested in each site, chuck it to our compiler such that we can give ourselves some C++ that can be used for application testing, chuck it into HLS to get some precision, to get some estimates. So this is what, actually in reality we're using HLS for, is to get these early fast estimates and prototyping before we actually maybe go and harden stuff into RTL. Well, harden, I suppose, is a bit of a weird term. And then, chuck it into our rover toolchain as a final interface to give us some really optimized RTL. So I guess in this setting, I think of rover as more of a super optimizer. And one thing that's really cool is that you're getting feedback at every stage of this design flow. So we can see, as we're making changes at each of these stages, we're seeing something new. One incredible gap that I've completely lied about is this doesn't exist. This IFP into rover currently only consumes RTL. So, we can ask questions, and exactly what the reviewer of this paper asked is, how do we actually communicate this information in a good way? What does rover really need to know to go and generate optimized RTL? What does your HLS tool even need to know to go and generate? Is really C++ the best way to communicate that intent? And so we can think about lots of different ways we might want to do that. But I think for that, I'll leave it there.